A few administrative things on the D2L announcements, right? We have posted the practice final exam, especially after you have today's content or whatnot. You have all of the knowledge for the entire course. And so you can go ahead and take that whenever you would like. And then there's also the post-course survey that's due next Wednesday. And so make sure that you take that sooner rather than later, just so you don't forget. It's worth a bit of extra credit. And so, yeah, don't forget to do that, similar to the pre-class survey. Before we get into the new stuff for today, a quick review of what you should have taken from the 10.4 pre-class videos. And overall, there are 3 big formulas in this section that you need to have under your belt by the time the final exam comes around. The first one is kind of some simpler area formula here. So area for some polar curve or some polar region. And you may wonder kind of why is the formula this way? And it's talked about a bit in the textbook, so a proof of this formula. You also really go into this in Calculus 3. This can be actually represented by a double integral. And so, yeah, Calculus 3 is all about multivariable calculus. And so polar and even higher dimension forms of polar come back. Something called cylindrical or spherical coordinates come back in Calculus 3. And so you really get to see where this formula comes from. And so for now, though, right, we got this formula and we'll apply it to lots of situations. So this is a relatively nice case scenario here. We also get something more complicated as far as area. And this is area between 2 curves, right? So, and this is very similar to kind of, you know what, like maybe 5.1, what we did at the very end of Calculus 1, kind of just before we came into Calculus 2, we did area between curves in Cartesian equations. And it turns out you can do something very similar for polar equations. And so you have a nice picture here, right? If I wanted to figure out the area between these 2 polar equations, these 2 polar curves here, right, we can have a formula for this. And so that's the second big equation. This is really what we're going to be talking about in Friday's class. So we're not going to get too much into this stuff. This is going to be the less nice areas that we'll be covering in Friday's class. So this one's kind of a bit on hold for right now. The other thing that we will be covering in today's class is going to be arc length. So this is our 3rd arc length equation for the class. We already have one for parametric curves that was kind of given first. And then we had an equation for Cartesian. That was the 8.1 that we skipped for a while and then came back to. And then here we have arc length for polar curves. And so we're going to practice applying that at the beginning of today's class a little bit, and then get into some area stuff. And that's how we'll finish out the entire course. Okay, so that's kind of right. Of course, we got lots of examples and whatnot throughout the pre-class videos, but those are the big 3 things that we need in order to succeed in 10.4 style questions. Any questions before we jump into our new stuff for today? Let's see, I don't see any raised hands. Oh, now one raised hand. Let's go ahead and call on you, Riley, and then we'll take some Q&A questions.
Hi, can you hear me?
Yeah, sure can.
So I just had a question about the very first example in the pre-class notes.
Okay.
So I saw that in the second line, there was a 2 out in front that we had to like multiply across. And then when you substituted the 1 plus cosine 2 theta in for the cosine squared,
yes,
I just was curious why you didn't multiply the 2 across there as well.
So yeah, so this formula that I was using in order to transform goes like this. It's the power reduction rule. It says cosine squared of u is equal to 1 plus cosine of 2u, all divided by 2.
Oh,
and so notice, yeah, there was a couple of things that happened. Of course, right, instead of just theta, we have 2 theta. The squared's no longer there. And yeah, kind of that 1/2 ate the multiplication by 2. And so they actually canceled. And that's kind of why that didn't appear.
Okay, thank you. I think I just missed that.
No problem. Excellent. What's going on in the Q&A, Yuan?
Yeah, there's one asking when we get collision points where functions intersect, we need the angle to plug into r sine and r cosine. And is plotting the only way to get at this angle?
No, so you don't need to necessarily plot in order to get the angle. You can solve these things algebraically. And so we won't be covering that too much in today's class, but really in Friday's class when we have multiple curves and we become very interested in when they intersect. We'll see it just a little bit today, but really a lot in Friday's class. Yeah, good question. Good. Any, maybe one more or so?
Yeah, there's one asking, I don't know, understand. Is the Webwork CAC 1 review and the drop dead review required?
Oh yeah, these are Webwork assignments. No, they're not. This has been asked in Piazza and answered there. But yeah, they're not required. No points associated with them.
Okay.
All right, excellent. Well, why don't we go ahead and we'll start doing a question or so from today's stuff, and then I'm sure there'll be more questions. So starting off here with arc length, and we're gonna be getting into some nice-ish areas. So find the length of the curve given by this polar equation, r equals a on the interval from 0 to 2 pi. So the big thing here is that we need to remember our arc length equation for polar curves. That is that we're going to be integrating with respect to theta. So of course our bounds should be theta bounds. Luckily they're given to us, right? Theta ranges from 0 to 2 pi. As with all of our arc length equations, there's a square root in them. And then remember it goes r squared plus and then dr d theta squared, right? So I'm just going to write r prime squared. And so we need to go ahead and substitute these things in. So in this case, my r is some constant here, right? It doesn't say exactly what constant it is. Maybe it's something like 3 or 5 or, you know, negative 100 or whatnot, but it's some constant a, right? So I'm going to go ahead and substitute that in. We're going to have a squared. And then if I take the derivative of a constant with respect to theta, really with respect to any variable here, you're always going to get 0, right? So 0 squared. And so now this is quite nice, right? Of course, when you add 0 to anything, you just get itself. And now we have the square root of a squared. And so whenever you take the square root of something squared, well, you get the absolute value technically. And we weren't told that a is necessarily bigger than 0 here. And so, okay, we'll leave the absolute value. And again, we're integrating with respect to theta. So again, maybe a is something like 3 or 5 or negative 100. And so then the absolute value of any one of those things will just be, 3 or 5 or positive 100, right? And those are all nice and fine and everything. But the big thing is that it's still constant, right? It's still some constant. And so when we integrate this with respect to theta, we get that constant times theta, right? If we take the derivative of this with respect to theta, we'll get back to where we started. And now we just need to evaluate this from 0 to 2 pi. And when we plug these things in for theta, right, we're just going to get 2 pi times the absolute value of a. And so this right here will be my final answer. And by the way, this should look quite familiar. And this is, an excellent starting question. Of course, they get a lot more difficult than this. But if you were to go ahead and graph this, right, r equals a. So that is no matter what direction you're looking in, you always go out the same amount, whatever this a is, right? So you always go out that same amount. Of course, when plotting this, looking in lots of different directions, always going out that same amount, that radius from the origin, right? You end up plotting a circle, right? So you have a circle where the radius, right, r, quite literally is a. And so if you ask what is the arc length of this circle, that's just, well, for circles, they have a nice name for this, right? It's circumference. What is the circumference for this? And we know that circumference is equal to the pi times the diameter, or if you'd like to, you can do 2 pi times the radius. And so it's maybe no surprise that we got 2 pi times the radius. And so, yes, this one's nice that you can actually verify our answers. Sadly, this will not always be the case, but it is nice, kind of intro problem for us to start with. Okay, let's at least set up for example 10, and then we'll maybe pause and see what kind of questions are out there. So here's one that's a little bit more full strength. Again, we want to calculate the length of this curve here. It was nice, and I gave a picture just so you can really kind of visualize what's going on. And let's see, it still gives us some bounds for theta, right? 0 to 2 pi. And so let's go ahead and do the setup here. So the arc length is going to be equal to the integral from 0 to 2 pi. Again, we're integrating with respect to theta because we're given a polar equation here. We're going to have the square root of, and now we have r squared. So this is going to be e to the theta. That's our r in this case. That's the curve that we're interested in. And again, we need r squared plus the derivative of r with respect to theta squared. And of course, if you take the derivative of e to the theta with respect to theta, well, the whole thing with e is that its derivative is itself. So this is quite nice here. And so we just have, well, again, e to the theta, and it's being squared. Of course, when you have powers raised to more powers, you can go ahead and multiply those, right? So you're going to have e to the 2 theta plus e to the 2 theta, right? Again, powers raised to more powers. And if you'd like to, well, these are like terms, right? They're the exact same thing being added to itself. If we wanted to simplify even more here, right, I could just add them, and we get 2 of those, right? 2 of these e to the 2 thetas. Again, this is all within a square root, and then we need to integrate. Okay, well, let's go ahead and maybe break this up here. When you take the square root of 2, you just get the square root of 2. It is what it is. And when you take the square root of e to the 2 theta, well, remember, e to the 2 theta, if you take the square root of it, it's like being raised to the 1/2 power. And again, when you have powers raised to more powers, they multiply together. And so that 2 theta and the 1/2 power are going to cancel a little bit, right? And you're just going to be left with e to the theta. And so this is quite nice. It's already positive, right? Normally you'd have to worry about some absolute values, but remember e, what it looks like, it's always positive. And so you don't have to worry about those absolute values. So now when you go ahead and you integrate this, well, the square root of 2 is going to be along for the ride. And the integral of e is itself, just like the derivative of e is itself. And then we need to evaluate from 0 to 2 pi. And so if we were to input 2 pi, there we go. And then we have to subtract away, well, 0. And so, okay, this is what our answer is. Or is it? I made a mistake. Someone tell me, what is my mistake here? Yeah, exactly. I was going too fast, right? But sometimes I see this, especially on exams and quizzes and stuff where, you know, kind of it's a little bit more high stakes and there's time pressure and all that sort of stuff. Be careful and just verify, right? When you plug in 0, do you really get 0? In this case, you don't, right? If I plug in 0, I get e to the 0. And remember, anything to the 0th power is actually 1, right? And so this right here is going to be 1, and it's still being multiplied by this root 2. And so really, I need to subtract away root 2 from my final answer here and to get this completely correct. All right, so that right there is the correct arc length for this particular problem. All right, good. Let's go ahead and take a few questions now that we have a couple of these under our belt. Anything going on in the Q&A, Yuan?
No, not for this one.
Oh, okay, great. Well, I got one more that's even more difficult than this. So we'll do that one, and then we'll kind of come back and see, maybe there'll be some questions from that. So this is our last arc length problem for the day, I believe. This is for the cardioid, right? So this curve here, 2 minus 2 cosine theta, that's what our r is given by. And still on the face of it, right, we still need to set up our arc length equation just as before. So L is going to be equal to the integral from 0 to 2 pi. That's kind of the classic stuff for thetas. So you'll see that quite a bit. We're going to be integrating with respect to theta. So those are theta values. And we're going to be taking the square root of a bunch of stuff, right? We need to have our r squared, and we'll need to take the derivative and square it. So our r squared, that's going to be our 2 minus 2 cosine theta. And when we take our derivative, right, of r, well, we would have -2, and then the derivative of cosine is going to be negative sine. So I'm going to go ahead and change that to positive there. So +2 sine of theta. Let me just kind of simplify that down there. All right, so that right there is our good setup. Now let's go ahead and evaluate this. And well, okay, I see that we have a binomial squared. And so I'm going to say, why don't we try to FOIL that all out and see if things simplify. I'm kind of hoping, right? I see a cosine, and that's inside of a squaring function, and I see a sine inside of a squaring function. So I'm kind of thinking in the back of my mind, right, sine squared plus cosine squared will be 1, and hopefully I'll be able to simplify things and life will be a bit nicer. And so, yeah, why don't we go ahead and expand this and see what we get. All right, so if we were to do the firsts, you would get 4. If you were to do the inners, you would do what? -4 cosine theta. If you were to do the outers, you would also get -4 cosine theta. And if you were to do the lasts, you would get +4 cosine squared theta. So that's me foiling out this binomial here being squared. And then with the sine squared stuff, well, 2 squared is going to be 4, and sine squared is just, well, sine squared, all under our square roots. And so here's what we were talking about, right? We see a sine squared and a cosine squared being added together. So I know I can simplify that. And we also see there's a couple of like terms here, right? -4 cosine, -4 cosine. So let's go ahead and combine those as well. And so let's see, we're going to have 4 minus 8 cosine theta. And let's see, cosine squared plus sine squared is going to be 1. But it looks like it's being multiplied by 4. So this is actually going to be +4, or 4 times 1. Actually, so now I see that there's another 4 in the front of all this. So I have 4 plus 4. Let's go ahead. I don't want to do another line for that. I'm just going to do 4 plus 4 is 8 and put them there together. All right. So now the question is, how do we integrate this thing here? And I think we've seen this type of integral maybe once before, but this one requires a little bit of a rewrite. In fact, the same sort of rewrite that we were talking about from the pre-class video stuff is that we would like to use this power reduction rule. Turns out to be in reverse, actually. So let me just kind of pull off to the side here for just a second and remind us that on our formula sheet, we have the power reduction rule for sine. Right? And it goes like this. Sine squared, if in particular when we were trying to integrate sine squared and things like that, this was equal to 1 minus cosine of 2u all divided by 2. And I bring this up because actually we're going to want to go backwards with this, right? We have something like 1 minus cosine, right? And if I could trade that in for a perfect square, that would be wonderful, because then it's going to cancel with my square root. And so I'm very interested in getting a perfect square instead of this 1 minus cosine stuff, just so that way it cancels with my square root. So let's go ahead and rearrange this a little bit. I'm going to multiply through by 16. I'll show you why this ends up being so nice. So if I multiply through, of course, on the left-hand side by 16, we just get the 16 out in front. And on the right-hand side, if I multiply by 16, well, it cancels with that 2 a little bit, and we're going to get 8 minus 8 cosine of 2u. And so by multiplying by 16, you can see that I've actually recreated this 8 minus 8 business, right? So that's really kind of what I was doing. You could also break this up into 2 steps. You could multiply just through by 2 first, and then say, well, I want those 8s. So I'm going to multiply through by 8. And of course, 2 times 8 is 16. So that's why this is just a hair faster. Okay, well, in this case, right, in order to get this formula to exactly line up, right, I have 2u is equal to theta, right? Because here in my case, I have cosine of 2u. Here I have cosine of theta. So to get this exactly to work out, right, I want 2u to be equal to theta. So that means when I exchange, right, in this case, I get 16 sine squared u, right? What is u? Well, u is going to be equal to theta divided by 2. So that's what I'm going to be inputting in there. So now I think we're finally ready to bring this back into our problem here. And that is, we found that this 8 minus 8 cosine of theta is going to be 16 sine squared of u. And again, u is the same thing as theta divided by 2. And this is still all in my square root. There we go. All right, now we can go ahead, right? We have the square root of something squared, so those will nicely cancel. And so let's see, we're going to have the integral from 0 to 2 pi. Square root of 16 is 4. The square root of sine squared is sine. And again, we should spend, a second or so thinking about, right? Normally, when you have squaring something and then the square root, right, you would have absolute values here. But notice with the interval that we're on, from 0 to 2 pi, if I was to input that into my sine function here, right? Well, notice you're dividing by 2. So that's really, when I input 0 to 2 pi, it goes from 0 to pi, right? And so if I think about on my unit circle, from 0 to pi, that is all up here. Notice from 0 to pi, sine is already positive, right? Sine is supposed to be the y values of the unit circle. So all of those y values, well, they're positive, right? They're above the x-axis. And so you really don't have to worry about, in this case, the absolute value, right? So the absolute value, it's already positive values. So the absolute value is not doing anything. So now we can go ahead and integrate this. When I integrate sine, I'm going to get negative cosine. And I need to evaluate from 0 to 2 pi. And then you yell at me, I've made a mistake. What did I forget? Exactly. So I need to have the chain rule. If you think about it from the derivative standpoint, that is taking the derivative to get back to where you started with, or it's a very small u substitution, right? Either way, you'll see that I forgot a 2, right? Because I need something that when I take the derivative of this theta divided by 2, right, I'm going to get this extra 1/2. I need something to cancel with a 1/2. And the right thing to cancel with a 1/2, multiplication, right, is going to be 2. I did see, just while I was peeking in chat for all of your answers here, why is the cosine negative? And it's because we're taking the antiderivative, right? If you were taking the derivative of sine, you would get positive cosine. But when you take the antiderivative, right, what do you take the derivative of in order to get sine, right? It's got to be negative cosine. Excellent. And so let's go ahead and finish this one up. Let's see, I have -8 once I put all of my constants together. And now let's go ahead and evaluate first at 2 pi. So this is going to be cosine of 2 pi divided by 2. So that's going to be pi. And we're going to subtract away when I plug in 0. So we're going to have cosine of 0. And so we're going to get -8, and cosine of pi is going to be -1. And cosine of 0 is going to be +1. And so, yes, we have -8 times -2. So this is going to be a +16. Notice if you didn't include that negative cosine here, you would have gotten the answer -16. And that would be maybe an indication that something's gone wrong, because after all, we're supposed to be finding the arc length, right? This is supposed to be the length of a curve. We know that the answer should always be positive. And so if you get an answer that's not positive, that's an indication that something has gone wrong in your calculations. And you need to go back and figure out where you may have dropped a negative sign. All right, so that right there would be my final answer. 16 is the length of this curve. All right, any questions here? Gabriel has his hand up. Go for it if you have a question.
Yes, Professor, do you hear me?
Yeah, sure can.
Okay, so this is a general question about length, but I know that we've been given, I believe, 3 formulas for length, right?
Mm-hmm.
And they all differ somehow.
Yep.
My question is like with all 3, what is like the difference between them, and like when should we apply what length formula?
Yeah, so they're all kind of stem from maybe the parametric version. I would say that's maybe the purest form of the arc length equation. So you can get the Cartesian version and the polar version from the parametric version. And when you should apply them really depends on the problem that you're given, right? If you're given a problem where you have a polar function, and it says, hey, what's the length of this curve? Well, use the polar one, right? So if you have a bunch of r's and thetas, that's when you should use the polar one. If you have the Cartesian, right? You have a Cartesian equation that says, hey, what's the length of this curve? Well, then you should use the Cartesian one, right? And if you have a parametric set of equations, then you should use the parametric one. So it's really whatever you're given, whether you're given something with r's and thetas, whether you're given something with t's, or whether you're given something with just x's and y's, that will determine what equation you want to use.
Okay, thank you.
Yeah, definitely. Good. All right. Well, with that, we are going to move on into the area portion of today's class. And again, this is nice-ish areas. For the most part, we're going to be talking about when we only have one curve. And so here we have this limacon, r equals 1 minus 2 sine theta. And we'd like to find the area inside of the inner loop. And so if you click on this here, I already was playing with this before class, so we'll navigate over here. It should take you to this Desmos graph right here. And so we can see, oops, limacon's kind of like a cardioid, but it has kind of an outer loop and an inner loop here. And so I have this plotted from 0 to 2 pi. And then I also have a little bit of code here that just kind of plots this around the curve and everything. And so let's go ahead. I'm going to hit play here. And you can kind of see where you are on this curve for lots of different theta values. Let me try to see if I can't zoom in and make this any bigger here. All right. And so you can see right now, it's only barely, you can see a little X on this curve. In fact, let me go ahead and I can go into this code to make this work. And I'm going to make this a little bit larger. I'm going to make it a 0.2. So 15. So it's a bit larger there. All right. So now you can actually see the point on the curve a little bit more clearly. So you can see that when you have this theta value here of like 3.14, right, where you are, the pi, where you are on the curve. And so we can see that we're on the inner loop. Let's see, where do we enter the inner loop? It seems like, okay, here we're on the outer loop. And then right around here or so, we get on the inner loop. And then we continue on the inner loop for a while, inner loop for a while, inner loop for a while. And then we intersect itself again at the origin. And then we start tracing out the outer loop. So if we want the area of the inner loop, we have to know when are we on the inner loop, right? And we become very interested in those theta values. So we need to be very interested in, let's see, this seems to be the largest theta value, somewhere around like 2.6 or so. All the way down, this is when we're on the inner loop, to this bit right here, right? So right around here, about a half or so. That's when we're tracing out this inner loop. So the question is, well, what are the theta values when we're actually on this inner loop? Because that's what we'll need in order to set up our integral to calculate out the area of just the inner loop. Okay, so we may come back to that in just a second. But let's bring back our notes here. And we can see that in order to go into the inner loop and out of it, again, we seem to be passing through the origin. And the origin is when the radius is 0, right? So that is to say, I would like to set up the equation. When is my radius? What theta values would make my radius equal to 0? Because that'll tell me how do I enter into that inner loop and when do I leave it? I always seem to be going through this r equals 0. And so when I set up this equation here and I go to solve, right? So maybe I have 2 sine theta on this side once I add that over, and then we divide by 2. Right? Now we get one of these classic kind of values on the unit circle, right? We know some theta values in which the sine would be equal to 1/2. That's going to be when theta is either equal to pi over 6 or when it's equal to 5 pi over 6. That's when our sine would be equal to 1/2. Which, by the way, if pi is around 3 and a little bit larger than that, well, 3 divided by 6 is around 1/2. right? So this actually is fairly close to, remember when we were looking at the Desmos graph, we saw that we entered in at about 1/2 and we exited at about 2.5-ish, right? So again, this is 1/2 times 5, so around 2.5-ish. So that's the first thing that we need to do, right? I guess I could have started with anytime that you have the area that you're interested in for one particular polar curve, right? We know that's going to be some setup here, an integral from a to b of 1/2 r squared d theta. So maybe I got a little bit ahead of myself, right? I could have gone and I could have set this up right here and done the 1/2. And instead of r, right, we're going to put an r value, 1 minus 2 sine theta, all being squared d theta. But at some point, you have to answer the question, what are my bounds of my integral? AKA, what traces out this inner curve, right? If I just want this inner loop right here, the area lying inside of that, I need to know where is the inner loop? What theta values correspond to that inner loop? And so that's where the graph really comes in useful here. And then we did a little bit of algebra in order to solve that. Our starting point should be pi/6. That's when we enter into the inner loop. And our ending point should be at 5 pi/6. That's when we exit the inner loop. So you can see sometimes the difficult part for this is setting up the integral, right? And so we need to set up the correct integral. And then of course, we will integrate this one and see it all the way through. But right, the setup is not as trivial as maybe the arc length was, right? For the arc length, it went pretty fast, right? Because they would tell you what's your theta starting point, what's your theta ending point. And so you just knew those things, right? So you can see with the area ones, they are a little bit more difficult of problem, I would say. Okay, before we get into the evaluation with this, I just wanted to pause and see if there are any questions about anything that we've covered on this problem so far before we get into evaluating. Covered that. Okay.
There's actually one I answered, but I think he probably wants to ask you, and it's asking, why did we solve for 0?
Why did we solve for 0? So yeah, that was the transition point. If I go back to my graph here, right, the transition point from when are we on the inner loop versus when are we on the outer loop, right? And so you can see that right now we're on the inner loop, but we're not there forever, right? So eventually, well, now, for instance, we're on the outer loop. And so if you want to know, well, when are you on the inner loop versus when are you on the outer loop, you become very interested in that transition, right? Well, when do you actually change from the inner loop to the outer loop? And then you become very interested about when do you pass through the origin, right? When do you have r is equal to 0? Because that's where you have this transition between the inner loop and the outer loop. And so that's why we set r is equal to 0, because it's kind of the gatekeeper, right? It's the one that separates the inner loop and the outer loop, is that you go through r equals 0. And so you need to know where that transition point is if you have any hope of just isolating only the inner loop. Good. And then I thought there was a raised hand. Yes, Jackson, you have the floor.
I just had a quick question similar to the one that was just asked, but so when you get sine theta equals 1/2, what happens if there was more than 2 values for half? How would you set up the integral? Like, how would you choose?
Yeah, so I would do based on the picture, maybe then, right? So if I was trying to redo the picture here a little bit, right? I know that I seem to be entering in at maybe this theta value right here. So this is my starting theta value. I'll say theta 1. And so I can at least say that it's in the first quadrant, right? So if you got maybe lots of different theta values, maybe you could restrict down to one just being in the first quadrant. And likewise, when I left, remember our theta value was over here. It was in the second quadrant. So if you got more theta values, maybe some of them are in the third or the fourth quadrant, you know that you could exclude those ones just because they're not related to, the inner loop in this case.
Okay, that makes a lot more sense. Thank you.
Yeah, definitely.
What
Well,
if, I mean, they can use it in our exam or quizzes use Desmos, right? How would they find the intersection points?
yeah, so this is, a very particular problem that I set up, which is good, I think, for learning and whatnot. I agree that this would be a difficult question for a quiz or an exam, right? Of course, having seen it before, that's going to help quite a bit. But you can see maybe some of my later questions like this. Find the area inside of one petal of 2 cosine of 2 theta, right? So we could provide a graph for you like this, right? And then again, you have to be interested in your starting and stopping points, right? And it seems like maybe after this theta value right here, whatever this is, it's not going to snap to being a straight line. I like it when it does that. There we go. Right after this theta value right here, maybe we start entering into the second petal, right? After that, maybe we're starting to plot out the points for this petal right here, right? And maybe kind of if you're, before this, you're on the petal beforehand. So sometimes a picture like this is quite useful, even though it's not interactive. So of course, this is something that we could place on an exam or a quiz. Here's another one in the less nice-ish areas where, again, a picture is provided for you, right? And worst case scenario is, well, 10.3. One of the big things that we wanted you to take away from 10.3 is being able to graph your own polar equations. So you can imagine a longer style problem where it has you first graph the equation. And then the second part of that is do some area calculation, right? Do some calculus, do a 10.4 style question. So that would be kind of the longer version of this. If the graph's not given for you, you do have the skills in order to recreate the graph yourself, but that obviously makes the question considerably longer. And so that needs to be accounted for if we were to make it into a quiz or an exam question, obviously. Good. Well, why don't we go ahead and finish up the evaluation for this one here. Pi over 6 to 5 pi over 6. Again, I'm going to expand out this squaring, right? And so I'm going to, I need to FOIL this all out. So the firsts, the inners, the outers, and the lasts, right? So you multiply all of those together here, and we're integrating with respect to theta still. We can go ahead and combine our like terms here. We can multiply through by 1/2. And I, kind of going down this list and thinking about, hey, I'm going to have to integrate these things coming up pretty soon, right? I know how to integrate 1. Good. I know how to integrate sine. Good. Here's another one. Okay. What's a little bit more difficult, right, is integrating sine squared. And so remember, this came up back in chapter 7 or so when we were integrating powers of trig functions. And we just talked about it here quite recently, right? This is where you want to use a power reduction rule. So thinking that, hey, I'm going to have to integrate this stuff pretty soon. Let me also do this power reduction rule here at this step, just so that way I'm well set up for actually integrating this coming up. So, okay, we will be integrating from pi over 6 to 5 pi over 6. I'm going to multiply through by the 1/2. So I'm going to have 1/2 times 1 is going to be the 1/2. This would be -4 sine theta when we combine those like terms. But remember, I'm multiplying by 1/2. So when I multiply by 1/2, that 4 becomes a 2. And then here, I'm going to go ahead and swap in. And let me do the 4 here. Let me not forget about that I'm multiplying by 1/2. And instead of sine squared theta, I'm going to go ahead and exchange in for my power reduction rule. So my power reduction rule goes 1 minus cosine of 2u. In this case, it's just theta, all divided by 2. So I combine my like terms, I multiplied through by my 1/2, and I use my power reduction rule. We can even see that there's a little bit more cancellation, right? We have a 4 and a 1/2 and another 1/2. So that's going to perfectly cancel out and just give 1 here. All right, now at this point, I think that we're finally ready to take the integral. So when I take the integral of 1/2 with respect to theta, I'm going to get 1/2 theta. When I take the integral of -2 sine, well, I'm going to get +2 cosine. Of course, double check. If you take the derivative of this, do you get back to where you started? Well, yes, the derivative of cosine is negative sine. So yes, that works out. And then here, let's see, I need to integrate 1. So I'm going to have a theta, and I need to integrate this negative cosine of 2 theta. And so when I integrate cosine, I'm going to get sine of 2 theta. And again, I need to remember the chain rule, right? The chain rule, or a very small u substitution, is another way of looking at that. And that's where this extra 1/2 comes from. Now, when I take the derivative of this to see if I get back to where I started, the answer is yes, because when you take the derivative of 2 theta, you get a 2, and now we have a 1/2 to cancel with that, getting us exactly back to where we started. Now we need to evaluate this from, let's see, our pi over 6 to 5 pi over 6 in order to get the final answer. So let's go ahead and plug these things in carefully here. So let's see, 1/2 5 pi over 6 plus 2 cosine of 5 pi over 6. And let's see, plus 5 pi over 6 and minus 1/2 sine. And let's do 5 pi over 3 here. That's, after all, 5 pi over 6 once we multiply it by 2. And now we're going to go ahead and subtract away, right, when we plug in pi over 6. So we're going to have 1/2 pi over 6. We're going to have 2 cosine of pi over 6 plus pi over 6 minus 1/2 sine of, let's see, that's going to be pi over 3. And now I'm just going to go through and just kind of make little side notes what we're going to be substituting in here, right? Cosine of 5 pi over 6, we're on the left-hand side here. This is going to be negative root 3 over 2. Let's see, sine of 5 pi over 3. So thinking about where I am on the unit circle here, need a little mini unit circle. Here's 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3. So I'm down in the bottom right-hand corner here. This is going to be negative root 3 over 2 as well. Cosine of pi over 6. This is going to be positive root 3 over 2. And sine of pi over 3, this is going to be positive root 3 over 2. All right, so now let's go ahead and hopefully this is our final line here. And we're going to try to simplify all of this stuff down. So we're going to have 5 pi over 12 is this first bit once that we simplify it. Then we're going to have negative root 3, which is the second bit once we simplify it. Really nothing to do here with the 5 pi over 6, so just leave that as is. We have minus a negative, so that's going to be plus root 3 over 4, right? Because we have this 1/2 here and the root 3 over 2. And then we're going to be subtracting away pi over 12. That's going to be this bit once we've simplified it. Let's see, we're going to have plus root 3 plus pi over 6. And let's see, this is going to be negative root 3 over 4. This is the point here where, I mean, you can certainly simplify it farther. We have more root 3s and we have, right, we could get common denominators and all that sort of stuff. But this is where I'd probably be tempted to either plug it into my calculator if I needed a decimal answer, like for a D2L quiz or an exam. Or, right, if it was Webwork, then you could type this in exactly as is, and it would be able to render that and tell you if it's correct or not. So this would probably be my ending point, really, for any of the situations. Good. Any questions with this here? Okay, well then, we can at least begin example 13 here, even though maybe we won't get it all the way through. Again, you can see that we're very interested in calculating out the area in just one of these petals. And so you have to start to get interested in, well, when are we on this petal, right? Versus when do we get onto some of these other petals? And then you see, right, when you kind of zoom in, that the transition points always seem to be, well, here at the origin, right? And especially if you were to plot this out, right, if you were thinking about it as like a 10.3 style question or whatnot, and you were to plot it out, right, first you would be on this one, then you would probably come down here, then over here, then up here, right? And this is kind of how you rotate around this curve in order to generate it all. And so all of that, like the transition points between the petals, is always when R is equal to 0. And so at some point, you're going to be interested in setting this equal to 0 and solving for theta. Now, before that, you can set up your integral, right? So we know that the area formula is going to be given by an integral from some a to b of 1/2 r squared. We're going to be integrating with respect to theta here. So we could set up, right, the integral from a to b, 1/2. And when we take our r, 2 cosine of 2 theta, and we square it, and we could even simplify and all that sort of stuff. And we can see this is what we're going to be solving, right? Now at this point, this is where kind of we get stuck then. Let's maybe simplify here. The 1/2 and the 2 squared, this is going to be 2 cosine squared of 2 theta. Right, at this point, we really need to know what is our starting point and what is our ending point, right? When are we on this petal here? And so, well, now you need to solve this equation. Of course, we can divide by 2, right? And get cosine of 2 theta is just equal to 0, because 0 divided by 2 is still 0. And then we can think about, okay, well, when is cosine equal to 0? And cosine is equal to 0, well, in lots of places, right? And we could start to write those down. In fact, I probably don't have enough room to fully answer this right here. Let me kind of maybe, I'm going to cheat using technology and just give myself a little bit more space. What could I plug in into cosine and get out 0? Well, if I had what I'm plugging into cosine, for instance, being equal to negative pi over 2 or pi over 2, right? Then, right, cosine of negative pi over 2 or cosine of pi over 2, that would give out 0. But also things like 3 pi over 2 and 5 pi over 2, right? Any odd multiple of pi over 2, also negative ones, right? Negative 3 pi over 2 also works perfectly well. And going on forever sort of deal. These are any of the things that if I was to input them into my cosine would give out 0. But notice that these are not theta values. They're actually 2 theta values, right? Because what's being input into cosine is not just straight up theta, right? It's 2 theta. And so if you would like to know what theta values would work out for this, well, you need to divide all of them by 2, right? So that would give me stuff like negative 3 pi over 4 and negative pi over 4 and pi over 4 and 3 pi over 4. And of course, right, if you were to kind of plot these, they kind of make sense, right? Pi over 4, right? I don't really see a place where I intersect the graph when I'm going out in this direction. I must be kind of at the origin here, right? And you can kind of guess that, you know, if you were to plot this in a 10.3 style method, right, you would get, this would be out here, and then maybe at this line, you'd be right here, and kind of it would get smaller and smaller R values all the way back to R is equal to 0. So pi over 4 makes a lot of sense, right? And likewise, 3 pi over 4, which is over in this direction, makes a lot of sense. And 5 pi over 4 in this direction, and 7 pi over 4, right? Any of these odd multiples of pi over 4 seem to be working out. And so we certainly won't have time to finish this all, but one good setup for this would be the integral from negative pi over 4 to positive pi over 4 of 2 cosine squared of 2 theta. This right here would be a good setup that would give you the correct answer. By the way, there are some Webwork questions and so let me say or here, that allow you and rely on the use of symmetry. And so you could make a good argument here that instead of finding this entire area, right, after all, we're interested in finding the area of one of these petals. You could find the area of a half of a petal like this, right? And then because of symmetry, we would multiply it by 2. So you'll see some Webwork problems out there that say, why don't we just integrate from 0 to pi over 4, right? And we'll multiply our answer by 2, right? Doubling it to give us the full area of the petal. So maybe instead of a 2 here, I'll do 4 cosine squared of 2 theta, d theta. Either one of these will yield the correct result. And so this certainly is an option. And, you know, in kind of a D2L style quiz or an exam, right, you could really use either one of these. Of course, when you actually go to evaluate it, you're going to need to use the power reduction rule. And that's how you'll do that. I'll finish up this problem and post the full solutions, you know, after class here today. I think we didn't, no, this is our last problem. Good. And so, yeah, I'll finish this one up. But in the meantime, you know, try to solve this problem on your own. Okay. With that being said, let's go ahead and take a few questions. And that's where we'll end for today. Let's see. Anito, you have the floor first.
So I understand the whole symmetry thing. However, could you explain again really quickly why it was pi over 4 or negative pi over 4 to pi over 4 rather than, you know, another pi thing?
Yeah. So, I mean, that's kind of, if you wanted to just isolate this right half side, right? Maybe you say, well, maybe, right, you don't have to use negative pi over 4 to positive pi over 4. This is one option. You could do 0 to pi over 4 to get just this top piece here, like we did before. And then you could get the bottom piece, right? You could go from 7 pi over 4 to 2 pi, and that would give you the bottom piece. But if you wanted to just integrate all in one piece, I'm going to allow for a negative theta value, just so that way it's just all one integral. It's a little bit nicer.
Okay, so it really, I guess, wouldn't matter as long as it's like the correct interval, if you will.
Yes.
Okay.
One of many correct intervals.
Yeah,
right?
yeah, for sure.
Yeah,
there's
so
you just pick the simplest one, pretty much.
Exactly.
Okay.
Negative pi over 4 to pi over 4 was nice because it's all one piece. Otherwise, you're going to need to integrate, you know, in maybe 2 pieces, 0 to pi over 4 and then 7 pi over 4 to 2 pi. So it's certainly possible, but a little bit more painful.
Okay, for sure. That makes more sense. Thank you.
Yeah, definitely. Good. Let's see. Matthew, you have the floor.
Yeah, where you multiplied by 2 for the symmetry, could you just put that 2 on the outside of the interval too?
Absolutely. Yep. Okay. In fact, you could take the entire 4 now to the outside, and maybe you would at some point.
Yeah.
Yep. Either one would be fine.
All right. Thank you.
Definitely. Good. And Jason, you have the floor. Having a hard time hearing you, Jason. We're going to go ahead and let Gabriel go first, and then we'll jump back to you.
Okay.
Oh, I don't know who I heard there.
Yeah, that's me.
Oh, okay, perfect. Jason.
I just my question isn't related to today's topic. Do you have office hours?
Yes, I have office hours today from 4 until 5 o'clock. And in general, they're Tuesdays, Wednesdays, and Fridays from 4 until 5.
Okay, I had a question about the project. Would office hours be a better time to talk about that?
For projects, I would recommend we have special dedicated office hours for projects, just because my office hours are open. And so typically, you know, it's more about the standard class content and Webwork questions and stuff like that. So I would recommend that you schedule some one-on-one office hours. And there's details for that on Piazza. It's near the top. It's one of the pinned ones that I think it just says like special project office hours.
Okay. All right then. All right. Thank you.
Yeah, definitely. Good. And Gabriel, what's going on?
Yes. So I had a question about, so when you were figuring out your bounds, my question is why did you want to set it equal to 0, your equation?
Well, how do you figure out when the pedal stops? Right? When are you on that shaded pedal, that first pedal there, versus when are you on another pedal? And so those sorts of questions, right, that you have to ask yourself in order to isolate that one pedal there, those sorts of questions lead you to, well, the pedal seems to stop. Maybe if I erase all of this stuff that I've accumulated here, the pedal seems to stop, right? It seems to get closer here. And then later on, right, then if you were to graph this, then you're going to be going on to this pedal next. Okay. So once you hit this point right here, well, that's when you stop and you're no longer on this pedal. And likewise, kind of when you're right, graphing this, for a while you would be on this one, and then you hit this point, and then all of a sudden you kind of continue that curve down onto, again, this pedal that you're interested in. Okay. And so again, this point here is special. That seems to be how we enter in to that pedal and exit that pedal.
Oh, okay.
And so, of course, we become very interested in that point. And that point is, of course, when R is equal to 0, right? We haven't taken any steps away from the origin.
Yeah. Okay. Yeah, that makes a lot more sense now. Thank you.
Excellent. Yeah, no problem.